thank you very much. First of all, it's been a very, very long time since the last time I had a talk in present, so I'm very, very happy about that. And as you will see, I'm going to present something that interleaves very well with what Alessandra has told us, especially for the things about relevance assessment, in particular implicit feedback, which is a thing that I would like to integrate in the task that I'm going to talk about. So I've been working on probabilistic models for text classification for a very long time, and in the recent past, I've moved to this very interesting research area about building systems for recall-oriented tasks. Okay, so IR systems that need to retrieve most, if not all, the relevant items. So it's a quite different situation, and you will see that also the time that you have at your disposal, it's different. So you can think about different strategies and so on. So okay, so it's about not retrieving all, or it's not about retrieving a few very good items on top of the list. It's about having all the collections and catch them all, which means that you really want to have a very, very high recall of objects that you're interested in. So how does this relate to the real world? Well, there are plenty of colleagues that are working in e-discovery, in the legal domain, and systematic reviews in the health domain. So these are situations where you have to retrieve most, if not all, for example, legal patents or prior cases in law, or retrieve all the documents that are related to some specific medical condition before you take some decision. For example, the Cochrane, which is one of the largest companies that perform systematic reviews in the health domain, state in the webpage that this work is intended to produce high quality, relevant, up-to-date systematic reviews to have an informed decision when you have to take decisions. Okay. So, for example, this is just an idea of how this systematic review works. So you have time, a lot of time. You may have also plenty of people working on the same topic. So, for example, suppose that you want to retrieve all the documents in PubMed that are related to low back pain. Okay, so you start, for example, with that query about disc herniation. Then you retrieve a bunch of documents, which is around 2,000 in this case. Now you have physicians, clinicians, experts in the domain who actually read the documents. So you have time to read the document, you have time to rethink about retrieving new documents or differentiate the strategy of retrieval. And for example, you may have missed something and then you change the query. So for example, the physical examination for lumbar radiculopathy, which is another situation for low back pain. Then you have 600 or something more documents to retrieve, and then you go on. So the question is, when do you stop? And that's the problem for that we are going to talk about today. So I'm going to divide this talk in 3 parts. The first part is about continuous active learning. So it's a way that it's a strategy that you can use, and it's been shown to work very, very well in these recall-oriented tasks, where you retrain your model as soon as you have new information. Because remember, you have the time to do that. It's not like a usual or traditional search engine where you search something, you read, and then you're done. Here you have a document, you have time to read documents, and maybe while the expert is reading the document, you can retrain your system according to the previous feedback. Then the second part is about how you estimate recall with limited resources, and this is one of the problems. Also, when we in this research area evaluate things, we sometimes forget the fact that we have limited resources in the real world. And then the last part is about what we are doing currently about query variant performance prediction. So what is continuous active learning? So just to give you a very brief idea of how this works. This is just a sketch of how things work or may work. It's not exactly this in every time. Not all the researchers perform this strategy. Could be slightly different, but this is the main idea. So you have this collection of documents, 5 documents in this case. Then you have your user with a query, for example, search something for low back pain. Then your IR system rank these documents, which is different from the 1, 2, 3, 4, 5 ranking. Then the user reads the document, gives some explicit relevance feedback. Then you store this feedback, and then the system has the time to re-rank everything if you want to. Then you also can work in batches of documents. So for example, some strategies use 5, 10, 20 documents before re-updating everything. But I really have to see these cases where you need batches of documents, or maybe you need an experimental evaluation to check whether 5, 10, or 1 document is better than a set of documents. Then the user again answers with positive or negative feedback. In this talk, I will talk about binary relevance feedback. So it's either relevant or non-relevant, but of course you can use also a graded relevance. Then you go on and go on. Okay, so that's the main idea. So you formulate a query, then you rank the documents or the remaining documents in the collection, assess, and then you give feedback. And then you continue to do this until, remember that we want to catch them all. And that's the problem. The problem is, when do we stop? Okay, so continuous active learning is a way to retrain the model according to the immediate relevance feedback that you have. The problem is, how do you know that you have obtained most of the relevant objects in the collection? So the second part is about estimate recall with limited resources, and that's the difficult part. So remember, the limited resources here may be, or there may be also other resources that I can think of. So it's time and money, it's the first two. So if you have a limited amount of time to read the document or to finish the task, you have to take into consideration that. If you have a limited amount of money to pay the expert or the clinician or the legal expert, you have to take into account that. You do not have always this unlimited amount of resources. So every time you judge something, you should take into account the fact that you may finish at some point the money or the time needed to evaluate and to assess the collection. So how do we build an effective system given maybe a limited time or a limited amount of money, or both, which makes sense, right? So it's a question of balancing the fact that maybe we want a system which is good to retrieve soon the relevant documents. But remember that when you do that, you're not actually capable directly to estimate how many relevant documents are still in the collection. Okay, so you may go the other way around. So why don't we start sampling maybe in some clever way, not just random sampling, maybe in a different way, so that I can at some point know that 10% of the collection will contain relevant documents. So if I know the total number of documents, I can do some very simple math and say, okay, if I have 100 documents, 10 documents will be relevant. But so far, as in this example, I needed to judge 10 or 11 documents to say that I need 10 more relevant documents, and I still need to find them. So I have to spend some time to estimate the recall. Is it enough? Or is it okay to do that? So it's a balance between the two. So it's a kind of guessing how much do you have to gamble in one way or another. You have to do, there's a subtopic here, which is not completely different from the rest of this talk, but it's very, very interesting to think about this problem in how do I optimize the resources to build the most efficient system that will balance the estimation of the recall and the number of relevant documents that I can retrieve. So we may add this sampling part, and I refer now to a very recent paper by Lee and Canulas from University of Amsterdam, TOIS. So as you can see, there's a ranking module, just as I showed you. Then there is a clever sampling module where you have an inclusion probability. So it's a probability distribution of picking documents, which is not uniformly distributed over, I don't know, maybe 1 million documents. It's just proportional, let's say, to the rank of the document. So it's easier and it's clever. Then you assess. Then you have the estimation module. At this point, you are able, with some level of uncertainty, to say how many relevant documents are still in the collection. And then you can improve this estimation by adding more samples. And then you decide at this point if you have to stop or not. So this is a very interesting approach to balance the fact that you want relevant documents as soon as possible, at the same time to be sure that you have reached some level of accuracy. On the other hand side, we developed this very, I don't know, greedy approach where it was like catch them all. So let's try to sweep all the documents that I have in the collection that is in an area which is favorable in terms of relevance. So this is the two-dimensional probabilistic model that I have been working on forever now. It's just a traditional probabilistic model where instead of one number, which usually represents the ratio of the likelihood, you split this in the two numbers, in the two log odds that you have, and you plot these two numbers in this two-dimensional space, and you're able to see things that usually you don't see with probabilistic model. And you see shapes in these two-dimensional models where you have, for example, in this case, green dots that represent relevant documents, red dots, the non-relevant documents, black dots are the remaining documents in the collection. So there are areas in this two-dimensional space that are more favorable for looking or for sampling relevant documents. So here it's simply, let's try to sweep all the most favorable area, and then we stop when we finish the model. So the idea of our approach is, okay, I fix a number of documents that I'm able to read, and then I stop no matter what. It's 100, 200, 500, 1000, but at that point, I cannot go further than that because I finished the resources. So we try to compare these two approaches. These are just the trends of our approach compared to this baseline, which is the baseline of two runs provided by the colleagues by University of Amsterdam. So it's a collection of 100,000 documents with 50 queries. It was medical task, so retrieving documents about medical conditions. So here we can see that the very good baseline used around 28,000 documents to reach a recall, an average recall of 0. So it's 85% up to 90%, which is good, right? And this approach is able to tell you that, okay, so you are very confident about the fact that you have reached 90% of recall for each of the topics. Okay, so you are confident about that. On the other hand side, it's the other approach. So let's try to sweep all the space of relevant documents, for example, 200, 600 per query, 1000 per query, and so on. So if we stop here of all the experiments that we have done, we are more or less around the same amount of documents compared to the baseline. And it's interesting to see that this approach, which is, I would call it greedy, because it's just go in this direction no matter what. Even it's favorable, but you don't know anything about the number of relevant documents. On average, performs much better. Okay, it's 89 against 0.94 recall. But if you think about it, it's very, very hard when you are very close to 100% to get that 1% more. So it's 5% difference, and it takes more or less the same amount of money or resources, okay? The problem here is that on average, this greedy approach performs better than the other, but I cannot guarantee that for example, I can tell to the physician that I'm sure that I have reached 90%. I cannot tell that. I just know that in this particular situation, if you give me 1,000 tokens of resources, I'm able to perform very well, but I don't know how many relevant documents I've missed. On the other hand, I know that there are still something missing, but I can tell you how many I have missed. Or vice versa. I can also say that I can reach more or less the same level of accuracy, 90%, by reducing by 50%. So instead of reading 25,000 documents, okay, let's put €1 for one document each. So I've spent 25,000 euros. What if I tell you, okay, I can give you the same accuracy with a little bit of uncertainty with, instead of 25,000 euros, with 18,000 euros. So it's a lot of money that you can save. However, you have some uncertainty. So in some cases, this uncertainty is not tolerable. And so you have to balance these two approaches. So here are just numbers of these experiments that we have done in the past. And it's interesting because the approach of estimating recall, it's also much better in retrieving good relevant documents at the beginning, at the top of the ranking list, or the first K documents that you read, much better than the other approach. But at some point, it decreases while the greedy continuous active learning keeps rolling and keeps gathering relevant documents until you have more, on average, more relevant documents compared to these other approaches. So it's not one better than the other, absolutely. It's just you have to think about how you can balance these two approaches according to the limited amount of resources. I'm stressing this part because it's usually we forget the problem of limited resources or how we evaluate things in the real life. So third part, it's about a different approach that we have been studying, and I will talk to you, and I will tell you something about this in a moment, about how you can bet on some of the variant of the queries that you can reformulate. So suppose that you have an information need and you start thinking about how I can express this information need using queries. Maybe you come up with 10 variants. Is there a way to say which of these 10 variants is better than the others if I have to start collecting documents? Because if so, I have I'm starting in a favorable situation when I start retrieving more relevant documents at the beginning, then I can use this information earlier, much earlier. So it's about, instead of having just one query, try different query reformulation and have different ranks. Now, of course, you can perform post-hoc evaluation. So suppose that you actually run this experiment using different queries, you have relevance judgment, you use evaluation collection like track, play. So you can do this in a post-hoc way, but how about doing this beforehand? So are you able to predict which one of these reformulations will perform better than the other? Or can you order them in decreasing order for some relevance measures? So this is a very nice work by Zucon and others from CIR 2018. It's about query variation performance prediction. So that's the problem stated, but I have just said that. And there are many approaches for trying to estimate these query performance prediction. And these methods can be pre-retrieval predictors, so things that are stored, let's say, in the statistics of the collection. And then you can use that to make a prediction, or also post-retrieval. So first you rank, you don't use any relevance assessment, but you try to see according to the, for example, the frequency of the turns in the top K ranked documents, whether there's any information that you can use to predict the effectiveness of that query. So there are plenty of them. And in this work, you can see a lot of comparison about these approaches. And this is one part. And then for a work that we have been doing in the last few weeks, we started from this very intriguing approach that was presented at CIGR 2016 by Uemoto and others, which is called SendBar. And it was a user interface and an approach to suggest a user during the search. This resembles a little bit what Alessandro was telling us about a few moments ago, about how to guide the user during the search, visually also, okay? So suppose that you have the information need in mind. You have the information need of a user, which is smoking cigarette, right? But we don't know actually what is the intent of the user until we see some feedback from him, right? So it could be, for example, smoking cigarettes related to probability of cancer, lung cancer, or could be much easier. It's about smoking or the price of the cigarettes. We don't know until we have some feedback from the user, right? So the nice thing about this approach called SendBar is that the user has these colored bars with different query variations proposed by the user and also by the system automatically. And then you have these colored bars where the user has the possibility to see an estimate of how much information you still have to look for in order to, for example, complete the task of retrieving information about smoking cancer risk, and so on. So this is a very nice way to see different aspects of the same information need and how much information there is missing in the collection, okay? And so they define, and also previous work before that, define the intent-aware gain metric. So you have the importance of a document, which means that documents that are relevant for a central aspect among all the possible aspects of the same query, the most important aspects must be weighted more than the other. So these are just initial hypotheses or principles that you can use to define this gain metric. Then, of course, highly relevant documents produce higher gain than partially relevant ones, which is reasonable. And also this last one is a little bit different from usual. It's something similar to diversity in IR. So suppose that you already have seen some of these relevant documents. If you see at this point a relevant documents in the cigarette price increase, maybe this is more important for the user compared to yet another relevant documents for disease caused by smoking. So it's the question of novelty. So it's that differentiating the results. So it's a relevant document, relevant for one peripheral aspect, could be at some point in time more useful than others. Okay, so these are the general principles of this metric. So just to summarize, before I go into the just 2 slides of formula that I have in this presentation. So you have the topic, the central topic that the user is looking for. Then you have the subtopics, so the different variants of the topic. And these variants, these subtopics can be clustered. And the most important subtopic is called aspect. Okay, so these are the query aspects. Okay, so within each cluster, you have one of the subtopic which is more important than the others for some reason or some metric. Okay, so that's the setting. So how do you measure the importance of a subtopic without having any relevant information beforehand? Okay, so it's a question of comparing the ranking of the reference topic T of the user. So we have a reference topic T in this framework, and 1, 2, 3, 4, 5, it's the ranking of these 5 documents, while one of these subtopics has this particular ranking. Okay, so the importance of a subtopic just takes the intersection of these documents and uses that formula, which is 1 over the rank of the documents and the sum of these ranks to compute the importance. So the more the subtopic contains documents that are ranked by the reference topic, the more important is the subtopic. And also, among all the possible aspects or subtopics, we have a formulation of a probability of that aspect given a topic, which is just a weighted average. So the more important is a topic, the highest probability for that topic, for that aspect, sorry. And then we have this, which is the most important part of this talk about query performance prediction, which is the gain. So the gain of given a reference topic in one aspect and given a collection of documents that you have retrieved, the gain is given by 1, which is the maximum gain that you can get, minus some products of elements, of single elements, which are given by the amount of relevance that that document can give you. Okay, so you subtract elements or bits of relevance according to how much this document is relevant. And this relevance is computed in this way. It's easier than it seems. So it's just take all the subtopics within a cluster. For each subtopic in the cluster, you compute the importance of that subtopic and you multiply it in the numerator by the relevance of that document. So if it's higher in each list of the subtopic, this relevancy will be higher. If it's lower in the rank, this will be lower. How do we compute this relevance as given D? It's just 1 over the square root of the rank of that document. So as you can see, we are not using any relevance feedback here. We are just using statistics and positions in the ranks in order to try to get an estimate of how much information we can obtain from that particular set of documents and that particular aspect. And this is just the final formula of the intent-aware gain that is used by Sandbar to compute those color bars. Now we started from this, and we started thinking, well, can we use this formula to as a proxy for query performance prediction? So in the work by Umamoto and others, so the Sandbar work, they define the amount of misinformation in order to color those bars and say what could have happened if the user had browsed more documents. Instead, we want to use the same information to predict whether one of the reformulation is more could be more accurate than the others according to some measure. So we have been submitted this work together with Guglielmo Fagioli, one of the PhD students of the group, and you can read the preprint version of this paper. So there are 2 important things that is missing, not information, is that missing from this problem if you want to use that in a recall-oriented task. So usually, if you think about it, you do not have this reference topic. You may have some evaluation data sets, some reference topic, but because just the data sets, it's built in that way. But usually, when you have users that interact with your system, you do not have a reference topic. You have multiple reformulations, and you don't know whether there is a reference topic or not. We know that the user has some information made in mind, but we don't know any reference topic. And our hypothesis is that for this particular task that we are talking about, systematic reviews, we have one single cluster of query variants. So we have one particular cluster of aspects that we are interested in, and we do not have different variants of the same topic. So these are our two initial hypotheses, and we just changed a little bit the notation, but nothing important here, so I will skip this. But one thing is important. I will talk to you about and will show you the results. So in the game formulation, as you can see, we have 1 minus the product of a series of numbers given a collection of document capital T. So if you think about it, this is 1 minus a number, which is the relevance of the document, which is between 0 and 1. So in general, you will have a product of numbers between 0 and 1. So in general, you have n multiplications of small numbers. So if D is large enough, the problem of the game, defined in that way, is that it will saturate 1 automatically, because it's going to be 1 minus 0.2 times 0.3 times 0.4. If you do it 100 times, it's going to be 0, the product, numerically. So we have a saturation that goes to 1 very, very quickly with this formulation. So we changed it a little bit to see what happens if we perform a mean of the game instead of this product. The idea is the same. So you try to average those relevances instead of multiplying them. And one last thing before I show you what happens with experiments, it's going back to the idea that there might be an aspect. So there might be one of the reformulations which is more important than the other, even though you don't know what is, or if there is a reference topic. So what we have thought about was to build a similarity matrix among the different query variants, but just building up this matrix of V reformulation and D documents, where D documents is the intersection of all the documents retrieved by at least one reformulation. So it's just, if you have 5 reformulation, it's a metric of 5 times all the documents that have been retrieved by at least this formulation. And then each value of this matrix, it's defined as the number of columns of this matrix minus the rank of the document of that particular query. So it's a sort of approach to say, okay, let's see what is the distribution of these ranks for each reformulation. And the idea is that we may find some reformulation which is closer than the others. And the reformulation that is closer to most of the other query reformulation will be what we consider the centroid of this matrix of variance. And we will use in information. So just to give you an idea, at the end, if you have 3 reformulations, this is going to be a symmetric matrix where the first formulation, we use cosine distance between this reformulation. For example, the first formulation compared to the second formulation, it's close 0.2 according to a cosine distance similarity, and 0.4 with the reformulation 3. So we just compute the sum of the rows or the columns, it's the same, and order the reformulations according to the sum. So what we obtain with that, it's an estimate of how close is one reformulation to the others. And we hypothesize that the closest, the variance which is closer to the others will be more likely to gather more relevant documents, just because it's in between all the possible reformulations. So it's more favorable in that sense. And we will use this reverse order to say whether one topic is better than the other. So we try to see whether these approaches work, so to use this gain metric and the variance of the gain metric in a recall-oriented task. So we use the CLE 2018 e-health consumer and search task. There are 50 information needs with 7 query formulation each. We do not have a reference topic. I mean, there is a reference topic, but we did not use this reference topic. There are more than 5 million documents crawled using a subset of common crawl. And we also have, of course, about 500 relevance assessment per information need. So we started by running some traditional query prediction performance. And here you can see just a few of them that are related to the paper by Zuccone and others. So just to see whether traditional query performance predictors can predict which of the query will perform better in the future. In this first example, we did not perform intra-topic query performance, which means that we took the 50 variants and we ordered them according to the recall. And then we compared them to the actual order of the same 50 queries using relevance assessment. And as you can see, this is the Kendall-Tau correlation with the optimal or with the true order of these 50, and we have a significant correlation with this ranking. So for the intertopic traditional query performance predictors work well, or at least they can tell you, they can order the topics in a reasonable way. On the other hand, just zooming a little bit, for intratopic traditional query performance prediction does not give any correlation. So this means that if I take the 7 reformulation and try to order them according to one of the traditional query performance predictor, I do not get any correlation at all with the true ranking, the true optimal ranking. So this is not useful. Now, we are still debating this with our colleagues because it's exactly at the opposite of the paper of Zuccone and others. So we are going to check, but it's a different collection. So we are going to check whether the collection can impact this. But the idea here is that if you use traditional query performance predictor, it's not, I mean, at least for this data set, I can tell you that it's not useful in the sense that you cannot say anything about which variant will perform better. So we try to do the same experiment with the original gain by Momo and others applied to the query performance prediction with the average gain that tries to solve the problem of the saturation to 1 and the similarity-based gain. So the interesting thing is that there is a good correlation with the original gain, but the strange thing, which is not strange once you understand the fact that there is a saturation, if you increase the cutoff, so the cutoff means that I'm looking at the first 100, 1,000, 10,000 documents. So I'm going deeper in the list of the ranked documents. The correlation decreases, which is a little bit odd because you are adding information to the system and you're less able to predict which query variation is better than the other. Instead, if we correct the saturation problem, we increase the correlation, which means that I add more information and I give the information to the system, and the system is able to predict better which are the most favorable query variation, and the similarity-based gain, which works even better. So just one last thing about to show you how the gain saturates to 1 very quickly. Here on the top part of the graph, you have the 350 queries. It's 50 information needs times 7 reformulation. And as you can see, for less than 50 queries, we have a reasonable difference in the value of the gain, while for the rest, for the remaining 300 queries, it's almost 1 or practically 1. And this makes the correlation also difficult, if it's not impossible, to compute, because we do not have any difference between the query variants. And that is the problem of the original game. This is the average game that we propose. So as you can see, it's smooth across the 350. And here at the bottom part, you can see the blue dots, which represent which are the topics for which the correlation with the optimal ranking of the topics is significant. So it means that we can predict with a very good accuracy which topics, which variants perform better. And that's for the similarity matrix, which is also even better in terms of correlation. This is just one last slide to show you all the possible combinations that we perform. So as a final remark, to conclude, we saw that traditional query performance predictors are not that accurate, but it's debated right now for recall-oriented tasks. So it means that this approach may not work as well as we may expect. On the other hand, we transformed a gain metric, which was intended for finding the missing information in a user perspective, and reuse that to build a system that predicts the performance of a query. And we also propose a couple of alternatives to this gain function, and we improved significantly the prediction, at least in terms of the correlation with the optimal solution. So where do we go from here? So now I told you about the fact that with an initial greedy approach, we were able to retrieve a lot of relevant documents without knowing whether we were missing some relevant, or how many relevant documents we were missing. This was, we needed to counterbalance this with a sampling approach. Now I'm adding this problem of the fact that you may use some optimal strategies to pick some of these query variations and maybe start jumping from one reformulation to the other according to some strategy. You can do that, because now I can show you that you have a way to estimate the importance of each reformulation. So this is all work in progress, and I'm happy to take questions. One advertisement slide. There are special issues now together with Evangelos Kanoulas. We are trying to get momentum on this particular topic. So we have one special issue at the Intelligent Systems with Applications Elsevier. It's about technology assisted review systems. We have just obtained a deadline extension, so you have still more than 1 month. And then we have a research topic at Frontiers, which is more about evaluation metrics and protocols for high recall IR systems. So we welcome you to submit proposals and manuscripts to this very exciting research area. As you can see, it's a little bit different than the traditional IR, high precision IR, but it's very interesting. So thank you very much. And if you have questions, thank you.
Thank you, Giorgio. So are there questions from home? I mean, online? No? No? Super clear?
Thank you.
No questions here in the room? No? Great. I mean, okay.
Okay.
We like questions. Yes? Questions? Great. Alessandro, please.
So first of all, thank you for your talk, very interesting.
Okay, you can hear.
Okay, perfect. So my question is about the matrix similarity for queries, reformulation.
Yes.
Can you elaborate a little bit more how you calculate the cosine distance? So what is the vector like? Just a bag of words?
No, it's even simpler. So I didn't spend much time on that. So every cell in that matrix, so suppose that the first row is the first reformulation, and the n columns are the n documents retrieved. It's an intersection of all the documents retrieved by all the variants. Then each cell is the difference between the number of columns, which is the size of the matrix, minus the original ranking in the first variation, which means that we are trying to rebuild a sort of re-ranked of these documents, but it's just used to compare this set of numbers. So it's not EF and EF, it's normalized without two, this matrix. But at the end, it's just comparing this sequence of numbers in this vector space of rankings to see whether one reformulation is closer than the others in terms of documents that have been ranked close to the others. So the idea is that if there is a reformulation which rank documents, let's say similarly to reformulation 2, reformulation 3, and 4, it may be more promising in terms of relevance because it captures all the variations. So that's the idea. So it's trying to capture the reformulations that tries to keep all the documents of all the other reformulations. That's the basic idea.
Okay, so a high score means you have very similar ranked list?
Yes. At least
Oh, sorry.
yes.
Yeah, a high score in
Yes.
the cosines means that the ranked list of one reformulation is very close in terms of documentation. Okay, thank you.
Okay, Giorgio, we have a question from
Yes.
home, and we can read it. So, Daniel Ebers, if you want to, you can ask the question live if you want. No, well, basically there is a lot of material to digest. The question
Yes.
is there something to read?
Now, I shared the slide on SlideShare. If you go on Twitter, I've shared the slides, and in the slides you have some of the references that I've put. And I can give you also some other, I mean, the 4 or 5 papers that I've mentioned in these slides, that are in the slides, contain a lot of background material, especially the work by Evangelos and Guido Canulas and Zuccon. You have plenty of material you can start with, and also our work. But it's, I think with these 3 or 4 papers, you can start looking around. And if you need more, just drop me an email, and I will be happy to give additional pointers.
Yeah, the webcam is there. So, yeah.
Yes, sorry,
Thank you.
myself. But, yes.
Thank you. Yeah, I was trying to digest what has been discussed. I'm not that expert on the matter, but I'm definitely interested in having all this knowledge, right? So it's, yeah, I just want to read more and understand a little better.
Sure. Thank you.
Okay, I write to you. Thank you.
Yes, please.
Thank you.